So we said deep learning is our attempt to replicate the human brain. Of course, the brain that we have understood up to this point in time. Let's first start with the most atomic, the most basic component of a neuron. So up here we have a diagram or a pictorial model of a neuron. So this is the most basic building block, or organic component of the human brain, right? We don't want to go down to subatomic particles and that kind of thing. So this is a neuron. It has these, let's say, branches called the dendrites that receive signals, electrochemical signals from other neurons. And these signals travel down these dendrites, and then they are processed by this thing called a nucleus. If the signal is strong enough, then another signal will travel down this axon and onto these other terminals. And it is at these terminals where we have connections with other neurons. So the way we are able to learn things and remember things is by these electrochemical signals firing off all of our brain. And so we have these neurons come together to form thoughts, to form memories, to form ideas. Okay? What you see here down here is a very abstract diagrammatical representation of the above. What we want to do is mathematically model this neuron. In deep learning, we call the neuron the perceptron. So in our brain, we have neurons. In deep learning, we have these things called perceptrons, which are supposed to be replicas of the neuron. That's a perceptron. So the dendrites, here are the inputs. What are the inputs? The inputs are the dimensions or the columns of the data. If you think, for example, about an Excel sheet, I can use that real estate example. Size of the property, distance to the city center, number of bedrooms. These are all columns, right? Column vectors. And each column vector is an input. And what's a circle? That circle is well, I'll show you what the circle is. It's a combination of two things. But it will be processed here. And then one value or one vector will be produced from this n number of vectors. So it's a linear transformation, in other words. And then here at the axon, you have the option of either outputting one vector or branching it out to three. Why do we want to have one or the other? Well, it depends on how we have structured the neural network. Let's look at a more mathematical representation of this model, and it's this. Here we have x sub 1 all the way to x sub n, where each x sub I represents a component of some vector x sub I. We notice the x's here are italic. So again, to use a real estate example, let's say the vector x sub 1 is the number of bedrooms. And then x sub 1 could be 3 bedrooms. Then the vector x sub 2 could be the size of the property in square feet. So this will be 2,000 square feet, right? So this could be three bedrooms, 2,000 square feet. So basically all of the values of the first property. Then we have these W's. Anyone know what these W's are? Any guesses what W stands for? Precisely, the weights, right? We said that these are all factors that influence the price of the property. But the number of bedrooms, the size of the apartment, the floor of the apartment, whether it has a balcony or not, its proximity to the city center, these are all important factors. but some are more important than others, right? So for example, being close to the city center is the most important factor. So for example, if x sub 3 is the proximity to the city center, then it will have a much higher weight. Whereas, let's say x sub 5, which is the, I don't know, the lighting system, right? If it's, if they use fluorescent instead of LED, it's very insignificant. It's something you can change, you know, in an hour or two. But let's say, for example, it's a factor. It will have a much smaller weight. What you do then is you take the product of each x and its weight, and then you sum. So you have product, and then sum of the products. That's the summation here. And then that value that you will get will be the activation. Now, this activation will be fed into what we call an activation function. And an activation function is basically a function that will determine the threshold of the signal. So if the signal is strong enough, we'll pass it on to the next perceptron. Otherwise, we will not send any signal. We will send a 0. For example, let me give you an example why you would need to choose an activation function, why you would need to process a signal or not. Imagine you're looking at a picture, and let me pull up a picture here. Picture of a character. Any character, doesn't matter. And we want to know what is the number in this picture. The way the model is going to look at this picture is to go through the entire picture. And of course, if you remember from session, I think our very first session, we said that pictures will be represented as matrices, right? This will be a matrix. And then we said a white pixel is 255 and a black pixel is 0. So if we, for example, look at this section of the picture, because we have to go from one corner to the next and process the picture one superpixel at a time. A superpixel is a collection of pixels. If we look at this superpixel, everything is white. There's nothing here. So its activation will be 0. There's nothing worthwhile. However, if we make our way here, well, now we will have a positive activation because we have a line. That's the idea. That's the purpose of this activation function. And when we use this activation, we will be able to narrow down our, we will have another linear transformation where we will only have the number 4 and we will discard the area around. And then later on, what we will do is we will flatten this matrix. We'll have another linear transformation where we'll go, for example, from a 16 by 16 to a single vector. So a 1 by 32 vector. Now, why do we need to do this linear transformation? We'll come back to this later. It has to do with distributions. We will leave that for later. Well, what I want us to first understand is this main component of the neural network, the perceptron. Now, why is it called a network? Well, because it's a network of perceptrons. If you take those, I think I was demonstrating something. That's why I have these here. Let me get rid of these. Sorry about that. If we take those perceptrons and put them into a network, we will get a neural network. So all of these circles that you see here, these are all perceptron, all of the perceptrons. It's called deep learning because, you know, we have these layers, and they can, if we stack enough of these layers, we will have a deep network of perceptrons. So that's why it's called deep learning. And this is an example of a fully connected network. And it's called fully connected because every perceptron is connected to every other perceptron in the subsequent network. Ron asks, are all the layers in this example are dense? Yes, this is densely, these are all dense, correct. Now, in a neural network, in a fully connected network, now there are different combinations. And why you would choose one combination versus the next will have to do with the nature of the data. Is it pictorial? Is it sequential? Like if you want to do time series is where, for example, like stocks, right? The price of the stock goes up and down. Or the weather. You want to see why does the weather go up or down? And see if you could predict it for the next month or the next week. Well, the change in temperature is associated with data, is associated with the calendar day, right? Obviously, summer it's warmer, winter is cooler. Or another example is, again, speech to text or autocomplete. You know, when you go to Gmail and you type in an email, you say, for example, hello, Ron, please see the, and then Gmail completes the remaining sentence. It will say, see the attached. It will like fill in the blank. It will complete your sentence. That is also accomplished using a sequential network. So again, I'll show you different arrangements. I'll show the pictures of them, but there are different ways we can assemble this. But here again, if you see here, we have the input layer, then we have a series of hidden layers, and then finally an output layer. Now, why does this have 4? For example, let's say you are doing, again, one more time, I'll do the real estate example. You have all of the features of the property, and then you're going to learn every single hidden layer in here is going to learn a weight. Basically, one thing I forgot to mention here, these weights are randomly assigned because the model does not know the significance of the number of bedrooms versus the significance of the proximity to the city center. To the model, these are all numbers. They mean nothing. So it will first randomly assign weights, and then using what we call backpropagation and a technique in multivariate calculus called gradient descent, it will adjust the weights. Basically, it will make one round of prediction, compare it to a sample. And then it will adjust the weights. Because if you remember, we talked about MSC in our last workshop. We said that we want MSC to converge to 0. If the convergence is 0, then what the model predicts and what the actual prices are will be equivalent. If the errors are 0, they will be equivalent. And that's what we want, ideally. Initially, the model, when we first feed the data to the network, the MSC will be large, but the model will keep looking at the sample again and again and again and adjust the weights. Adjust the weight again and again and again and again until it has understood why one feature is important, why another feature is not important. Now, again, if you're just trying to predict the number, you'll have only one output, which will be the price. If, however, we're doing something like CRNN, a convolutional neural network, where you're going to go from a matrix data to a vertex, to a vector. If you're going to be doing this transformation, this linear transformation, then what you will append at the end of the output layer could be another network. You can actually mix 2 networks together, especially for complex problems.